Welcome to the course on FPGA based signal processing systems. Continuing with the combinational logic circuit synthesis, as we'll also deal with sequential logic synthesis in this lecture. So, the don't care conditions, how those are considered in the synthesis process and in the realization also. So, if there is a case statement or if statement or the conditional assignments like ternary operator uses the combinational logic. If the in the synthesis process, if using these three would yield similar results, that is simulation results will be same if you are able to do the code same thing with case, if and a ternary operator. If the problem would be only the default assignments. So, if the default assignment is there in the case, yes, it will lead to 0 or 1 value. Else, if else statement is there, yes, it would also has 0 or 1 value, or ternary operator as well. So, this can give similar results if the default cases and mutually exclusive conditions are specified. Suppose if it is not, it will differ for x and z values. Suppose we have x specified somewhere in the default case, z specified, then the simulation results won't be same, okay, if you use them. So, x and z are the don't care and the high impedance states. In the simulator you can get this x as x itself, and z as the is going to be z. So, whereas in the synthesis process, how these two are getting changed. So, the case x, suppose case z, which is written over in the case statements, are treated as case statements only. If you have this explicitly assigned x and z, these are treated as don't care conditions for the minimization of equivalent Boolean expressions. So, to minimize the Boolean expression, the logic of the circuit, this x and z are considered to be don't care conditions if you specify in the Verilog code as x or z, and the simulation will give x in simulation, but in hardware it is either 0 or 1. So, the Verilog code which contains x in the which shows x in the simulation, but in the hardware it should take either x 0 or 1 value. So, in that case the assignment to x, what is that, in a case or if statement, will be treated as don't care for the synthesis process. So, again the conditional operator assigns value z to the right hand expression of a continuous assignment or in and in the level sensitive behavior, this will be synthesized into combinational logic. Let us see that the z assignments, how this is going to be synthesized with the tri-state buffer. Okay. So, the absence of default statement again needs to be considered, it would infer a latch. As I told you, that won't be no more combinational, you will have the latch inferred synthesized output. The level sensitive behavior will synthesize into combinational logic if it assigns a value to each output for every possible inputs. So, always at the rate A or B or C, and that A or B or C should be input. The sensitivity list should contain the inputs or input all the inputs, and those for all those inputs, what is the output should be specified within the always block. If something is missing in that operation, that is A or B or C, but you are not using that A inside the always block, then what is, if A changes, what should be the result of that code needs to be specified. So, every possible input combination should have an output in the level sensitive behavior. Also, default case default statement should be there, otherwise it would infer a latch, and the conditional operator z will be taken care as assigns a value to this, will be a high impedance state, where x is in hardware considered to be either 0 or 1, but in simulation it is x. So, now coming to the level sensitive behavior. In this example, we have this is actually the combinational logic. Input enable there is an operation code and a data A and data B. Output is the output of the ALU processor. So register, it has a ALU reg is ALU reg. The output is declared output is declared as ALU out. You can see the ALU reg which is used in this also. Assign ALU out. You can see the assign and always statement in one module. Assign ALU out enable equal to 1. If that condition is true, assign ALU reg, which is the register. Here it need not be the case. ALU register is assigned to ALU out or 4-bit high impedance state. Always at the rate opcode data A or data B. What is the opcode? 3-bit 001 ALU register. So because this ALU register is used in the inside the always block, this is declared as reg. So we use the data A or data B. The R of this inputs, assign it to ALU register. ALU register is XOR of A and B if the code is the choice of case or case item is 010. If it is 110 3-bit, then this is the opcode 3-bit here and not data B. So default whether you assign X or 0 depends on that the code the synthesized output will be the technology output, and the RTL analysis also will give the different diagram schematic and N. So the here if we 4-bit be 0 or 4-bit be X. Okay. So the case statement is first case statement has only 3 cases if you see, but opcode is 3 bits. Either you specify all the bits, all the choices here, or it should have at least a default statement. So all other cases the default will be executed. That means there is no issue in that. Either default is missing or all the conditions are not written considered here, that would infer a latch. So this case X and 0. So if this is X, okay, so what is the schematic here? So this has a 3 input here, having the RTL mux for ALU register, and there is a XOR and OR gate, also the inverter. So here XOR, OR and inverter 1, 2 and 3. These 3 options are given to mux. Okay, so the opcode which is having the 3 select lines, you can see the 3-bit select line is taken for the mux. This is synthesized into a mux. Also you can see that synthesized into a mux because it has all the the default condition is specified, though all the combinations are not listed over here. For other cases default would be executed. So in that case it is fulfilling the conditions which are to be going to happen in this. So it is realized into a mux, and the mux output also you can see ALU out equal to, that is what is ALU out, if ALU register will be ALU register will be stored to ALU out if enable is 1, otherwise 4-bit Z. So this assign statement getting realized here. So this output of the mux, okay, which is the ALU register, and if enable is 1, there is a tri-state 1, assign it, otherwise there should be a high impedance state. So this gets realized there on seeing the Z. So the RTL schematic understands that is going to be the tri-state buffer. Okay. If we use 0 in this case instead of X, because we use X, this X is considered to be a don't care, and in the minimization process if we consider X, there will be the synthesized output will be less. So resources used for the synthesized output will be less, whereas if you consider 0, it will have certain condition, it will have more components in that. Maybe we can show you that as well. So this here X representation helps in minimizing the minimizing the schematic or the logic. Where if you use 0, it will be more elements for a particular code. So the RTL schematic shows the mux structure, which is the case statement is realized as mux, synthesized and as a mux. Here technology schematic, it uses the 5 input LUT as well as this ALU out, that is you can see, and it gives the buff here, this the ALU out here, which is having the tri-state details as well. The tri-state enable, then go to the enable, it is 1 or 0, then the tri-state realization is here with the buffer. This is O buff, you can see value out O buff T, that is tri-state, mentions this tri-state. A lookup table, and there is one more lookup table for this also, LUT1, and then there is a tri-state buffer in the technology schematic as well. Each has the logical synthesis. Also we have the buffers for each data bit A and data bit B, A and B, whereas this opcode 0 to 2, 1, 2, 3, all of them are listed over here. 3 bits are connected over here because it shows the buffers with three bits for each one, for the each buffer takes care of the each bit here. So that is giving the technology schematic. You can see the truth table of this as well. So the realized 5 input LUT, and then this is the tri-state buffer doesn't have this, and either that LUT have 0 or 1 only. So it has 0, 1 input LUT as well as an enable. This gives the truth table of the logic which is used in that code. So if X, that would get minimized, and if we 0, then it would, the components would be more in that case. Sometimes this don't care conditions helps in synthesis process to minimize the logic resource utilization also, and at the same time the functionality should be preserved. So coming to the sequential logic with latches. So we have the synthesis process which has the which can infer latch in sequential logic. So latches usually whether in the code it is intended or not. Okay, so if it is intentionally we are making that we want a latch to be realized, suppose for a D flip flop or D latch, not D flip flop, if you have this then the realization is something that edge sensitive ones. In the level sensitive D latch one, you want to write a code, yes, okay, that is an intentional latch. Something is, if you miss the default case in a case statement, then that would form a accidental latch in the code. So there are two ways of synthesized latches can be observed in the output of the schematic. So a feedback free netlist in the combinational primitives will synthesize into latch free combinational logic. That is, as we said in the NAND gate in the combinational, if you don't have feedback, yes, there won't be any latches synthesized. So continuous assignments which we had already, that will be realized into combination logic, and it should not have the feedback in that. Okay, otherwise it would form a latch. Let's see this assignment statement, how it is giving the latches also. Feedback free continuous assignments will synthesize into latch free combinational logic. So if you don't have feedback in the assignments, continuous assignments, yes, a set of feedback free assignments also will not have the latches, or it will be synthesized into combinational logic. A continuous assignment using conditional operator, if with feedback, will be synthesized into latch. So we see the examples of them. So here assign statement with feedback. Suppose in this example module, input set, reset, output q and q bar. So you have a block where it is S and the R, I put set and reset, what is written over here, and then q and the q bar. Okay, this is it. So this module assign q tilde, that is set and q bar. So set and q bar are and tilde is inside it. set and q bar are and tilde and assigned to q. Okay, so that is assigned to q here, which is it's not a this is inside. Okay, so this, consider this diagram is inside, so it's not output connected to q, so it is it is inside. So that next statement, assign q bar, this q bar is getting input reset and q, which are ANDed and the AND function, and then tilde, it's getting this q bar assigned to q bar. So in this case, what is the feedback here? Okay, so set and q bar is getting q, whereas next statement q bar is getting reset and q. So reset and q is updating q bar, and then that q bar will be used here in this q bar here to q. So there is a feedback over here in this case. So this feedback, how does it get assigned in the synthesis process? Let's see RTL schematic: reset and then set, where it is taking, you can see this q bar q and reset, and it is given to q bar, whereas q bar output and the set are given to AND logic and then taken the invert. So there is a feedback over here and feedback over here. So this RTL schematic will have the feedback. So then it is a latch which is storing the set and reset latch we have. So this is nothing but NAND gate, one NAND gate, and this is another NAND gate which has the feedback. So it is a latch here, so SR latch. So the latch should be formed. This is because of the feedback, though these are combinational circuits, like the gates used in this is AND and NOT, but there is a feedback in this which is synthesized into a latch. And technology schematic also shows this. This is q bar LUT and the q here LUT, 3 input LUT and the 2 input LUTs using q and q bar. So this process, you can see that is the output, it's coming over here and it is going in as an input to LUT1. So there is a feedback. Okay, so from here, this is you can see the feedback in this process. So it's a technology schematic, and it's truth table, where the logic expression, Boolean expression has been obtained, like invert of I0 plus I1 and I2, invert of I0 and invert of I. So this is the minimization done in the synthesis process. The LUTs are being used for it. So that's a latch formation due to the feedback. And the code in which we had written that itself formed the feedback. So feedback free will be synthesized into combinational, otherwise this becomes a latch of sequential. So the accidental latches, if you consider the action, so consider what are the cases in which this accidental latches can occur. For this here, and the Verilog description should have to be realized as a combination logic, then it should have the ascend value. All the outputs should have the possible inputs, that is the possible inputs are to be specified, and a corresponding output should be specified, otherwise it would infer latches. So for example, input select A, select B, and data A, data B, output reg and y out. So always at the rate 1, 2, 3, 4, there are 4 inputs here. Case statement, select A and B, concatenation operator. Select A and B are 1 bits, so it will have the combination of 0, 0, 0, 1, 1, 0 and 1, 1. Here you have this 2-bit 1, 0. What should be the y out? Y out is data A. Okay, so if you have 1, 1, 0, then it's fine. If you have 0, 1, this assign data A, B. End case. So you see, this code is definitely incomplete because of the 0, 0 is not specified and 1, 1 is not specified. Moreover, default case is not specified. It's okay if you don't give this combination at this here, but specify the default case so that it won't be a formation of latch. In this circuit, when we see the RTL schematic, you can clearly see the latch which is inferred over this because of missing the default case. So data A, data B, yes, if the select bit is given, okay, so data A and data B can be selected. here. Okay, and the A and B 2 bits are going, select A or select B 2 bits are going to these marks, and the 2 cases 1001 are, it is considering default here is a 0, and then gives it to the ground. Okay, so that is inferring the latch because of the missing default case. The technology schematic also realizes that output reg I, reg 2, LUTs, and then you have this LD, this is a clear, and GE, that it is the latch which is inferred in the technology schematic as well. So, the Boolean expressions what we get from the synthesizer is that, and the truth table of it, this expressions are used in the realization process, the synthesis. And then if we come to the intentional latches, this the case was this, because of default case missing, that is an accidental one, that is we never intended to, or the formation as again. Similarly, in the if else statement as well, if we miss the else statement, it would form again. So, synthesis intentional latches, what are the, yes, want to have the latch in. So, data out with feedback in an if statement in a level sensitive behavior is, so for example, the input latch enable, input having data input, and output 4-bit data out, always that latch enable or data input. So, this is 1 bit and the 4-bit input, any one of this, any bit of data in or this changes, that is a sensitivity list, contains all the inputs. Yes, here if latch enable is true, is what is the data out, data in is assigned to data out. Yes, the condition is satisfied, the 4-bit data assign it to data out, else data out equal to data out. So, that is something how we can, this is inferring the latch, that is the feedback, else data out equal to data out. So, this is with feedback in an if statement. Okay, so how the synthesis RTL schematic shows, it is showing that RTL latch. So, data out is going to data out, and the data input is there, latch enable is there, it is complete, it is giving them structure which is the latch. And the technology viewer, you can see that technology schematic also have this LTC, each bit data out 0, 1, 2, 3 is inferred latch in this case. So, it is, we cannot assign this the condition, for the condition data out is going to be data out, it is going to be a feedback here in the inside the if statement. Yes, else condition is specified, so it should not, but there is a feedback in this. And the other example of this intentional latches, you see the event control expression of level sensitive behavior is sensitive to both latch enable and data in, but if condition is incomplete. Let us see that example here, input latch enable, input 4-bit, and then same the case which is considered in the previous one, always latch enable or data input. If latch enable is true, data out is equal to data in. Here also the latch will be in realized because of the missing else statement. Okay, this is incompletely specified. If latch enable is true, yes, input is assigned to data out, whereas else what is to be done. So, that is not specified. So, it would infer a latch again. So, this gives the latch RTL latch for this case. Both are it is good we have this input and latch enable if condition, but else is missing. With else is there, but if there is feedback, that would also infer a latch in the sequential logic synthesis. So, data register 1, 0, 1, 2, 3, the 4 bits infer latches in this case in the technology schematic as well. So, if statement, suppose that is completed with feedback is equivalent to conditional assignment statement, that is if you say in the if statement, that is what is the for example, in the previous example, latch enable is true, data input should be assigned to data out. Else, if latch enable is not true, then what is the data out should be? Okay, it should be specified. So, but here this data out equal to data out, like the else condition is there. So, if else condition is that, if else condition used in the previous examples is same as this assign statement here. Assign to data out. If this latch enable is true, data input assign it, else data out is assign data out to data out. This is forming a feedback again, but the if condition, if else condition is satisfied. So, this assign and if else condition both are equivalent. So, this would also infer a latch. In the case if we synthesize it, this it would infer a latch here. So, the latch inference is due to condition missing, which will in the else condition or default cases, the outputs or every input is missing, that would infer a latch in the sequential logics, that is accidental latches. If feedback is specified intentionally, then it becomes this, that would also infer a latch, that is intentional. So, how the for loop gets synthesized into the code. Suppose for example, module x in and input is x in and y is the output. Some parameter word length of 4 is specified, to just say 0, x in is word length minus 1 0. So, that means 0 and this would be 3, 0 to 3, x in is 4 bits. Okay. Output reg y and integer k. So, always at the rate x in. So, x in is 4 bits now. So, these are all coming into the sensitivity list. Yes, begin check for 1, y equal to 0. So, 1, where is there any change, assume y equal to 0, and this is the algorithm with this level sensitive behavior. The output, this is x in is either 1 or 0, that is what it is meaning here, level sensitive, and the cyclic behavior in the sense it is going to be a always block. So, the output is assigned to 0. Okay. So, then we what we do, check the inputs here for k up to the k word length minus 1, that is 2, 3, k equal to k plus 1. If x in k, that is 0, 1, 2, 3. Okay, x in of 0, 1, 2, 3, any one of every time the k is incremented, k is as an integer, declared as an integer. So, k in x in k equal to 1, checks for the bit, and then y assign y equal to 1. So, that means here this is for the disabled check for one end, it may be end and end. So, this is one here it is, this is a loop which is testing any one of the input is input bit is 1 or not. So, for loop, if an input is 1, the output is set to 1 here. Okay, if any one of the input, this is the description of the this description synthesized into combinational logic. The for loop is there and always at the rate x in is at the sensitivity list. But if you see the loop index k, which is eliminated in the synthesis process, and it has no hardware equivalent or hardware counterpart for it, but the whole code will be synthesized into a combinational logic instead of a sequential logic. So, here let us see, that is the for loops here, not the because always at the rate when we say at x in, you are assigning y equal to you can see that one more case here, y is 0 and output is declared as reg also, it should store because it is used in the always. So, y need to be stored or not. So, in that case this, though it is declared as y is declared as reg, it will not be a storage element. Okay. So, and the loop is completely eliminated in the hardware counterpart, and we should also see that y, which is declared as register, it does not synthesize into storage element. It would be just a we can see here the schematic, it uses the 3 mux, okay, for the conditions specified, checking the 0 to 3, that is 4 bits all of them, giving this as a select line. If this is 1 and checking each bit how the for loop is getting synthesized, you can see that it is removed, but the logic is here. If we have giving each bit has been given here 0 to 3 as a select one here. So the output yi and the yi, this bit is also taken here, one bit is s is taken as default, so only realizing 3 mux here. And the technology schematic takes the four inputs and one out this output, 4 input LUTs, and the 4 inputs are specified 0 1 2 3. All the 4 bits of the inputs are taken in the synthesis process. Only thing is the loop behavior will be eliminated. Instead of that, that will be realized as a combination logic. Okay, that's not like iteration and storing that value. Here it is going to be a combinational logic instead of a sequential logic. So you can see the output. Yes, if there is any one bit is 1, yes, the output should be 1. Any one bit is 1, any one of this, output is 1. So that function has been realized, okay, through the LUT, but as a combinational logic. Here is though any one of the input is 1, our output is all assigned 1. So with this we have a few examples of the sequential logic synthesis. Also we would take the synthesis cases, not only the latches, and what would be the output declarations mandate. If you don't declare this as an output, what would be the synthesis the code, how it will be synthesized, what would be the schematic. We'll see them in the next lecture. Thank you.